Good morning, everyone. Welcome to the session on secure outsourcing. We have three amazing talks lined up. So the first talk will be given by Shani Ben David on probabilistically checkable arguments for all NP.
Thank you, Akshay, for the introduction. So I'm going to talk about probabilistically checkable argument for all NP. I'm going to start by defining probabilistically checkable proofs, PCPs, which are well known from the famous PCP theorem. So in PCPs, we have a relation, which we think of as NP-hard relation. We have the prover and the verifier. Now the verifier gets both the instance and the witness as an input, and the verifier gets only the instance. Now the prover generates a proof, and the verifier, who wishes to verify that the instance is in the language, verifies the proof by querying only a small number of bits from the proof. So even if the proof is large, the verifier reads only a small number of bits from the proof. So for any XW that are in the relation, the probability that the verifier accepts an honestly generated proof is 1. Now, for the soundness, we say that any prover, even computationally unbounded prover, will not be able to convince the verifier on a false statement with probability more than half. Now, the famous and celebrated PCP theorem said that we do have PCPs for the entire class of NP. This theorem does not rely on any assumptions. And for the efficiency parameter, the proof size is quasi-linear in both the instance and the witness size, and the verifier makes only constant number of queries to the proof. Now, note that even that the verifier makes only reads only constant number of bits from the proof, the running time of the verifier is polynomial in both the instance and the witness. Now, in this talk, we're going to focus on a specific setting in which the instance is large and the witness is small. Now, there are many relations where the instance is large and the witness is small and vice versa. Just to illustrate what kind of relation has huge instances and small witnesses, we're going to see an example. Now, our example is ORSAT. In ORSAT, we have capital N sub-formulas. When we think about capital N as huge, so we have many sub-formulas, and each sub-formula is small and has n variables. Now we define our instance, phi prime, to be the OR of the capital N sub-formulas, and the instance size is at least capital N, which is, let's say, n to the 100, or even super polynomial in n. And the witness size is small, and why is that? So in order to satisfy phi prime, we only need to show we only need to give a witness to a single sub-formula. So the PCP theorem implies that ORSAT has a PCP with proof size that is quasi-linear in both the instance and the witness size, which is quasi-linear in capital N, which is super poly in N in our case. Now this is too large. Well, with this motivation in mind, Kalai and Raz introduced the new notion of succinct PCPs, in which we want the proof size to be proportional to the small witness rather than the huge instance. And specifically, we want the proof size to be polylogarithmic in the huge instance size and polynomial in the small witness size, and we still want the verifier to make only constant number of queries to the proof. So I just want you to note that we do not expect the proof size to be sublinear in the witness size, as this would contradict the exponential time hypothesis. But since the prover and the verifier both get access to the instance, we could hope for a proof size that is sublinear in the instance size. So succinct PCP would have implied that ORSAT has PCP with proof size that is polylogarithmic in capital N and polynomial in L, which is, in our example, essentially polynomial in N, which is small, where PCP theorem implied proof size that is super polynomial in N. So the question is, do we have succinct PCPs for the entire class of NP? So Fortnam and Santana in 2008 actually proved that succinct PCPs for the entire class of NP actually implies that the polynomial hierarchy collapses. So we do not expect to have succinct PCPs for the entire class of NP, but this is not the end of it. So we want succinctness, we want proof size that is small, and we want constant query complexity for the verifier. So what can we relax? PCPs are actually information theoretic primitives, so what about the computational analog? So Calais and Raz in 2009 introduced the notion of probabilistically checkable argument, PCAs, which are the computational analog of PCPs. Now in PCAs, we have a CRS. We have, again, prover and a verifier. The prover generates a proof, and the verifier, again, verifies that the instance is in the language by querying only a small number of bits from the proof. So if X and W were in the relation, then for an honestly generated CRS, the probability that the verifier accepts honestly generated proof is 1. For soundness, so now we talk about computationally bounded prover. So any computationally bounded prover, given an honestly generated CRS, can't convince the verifier on a false statement with probability more than half. Now this is the main difference between PCP and PCAs. And so the question is, do we have succinct PCAs? Now we relax soundness. We don't have succinct PCPs, but do we have succinct PCAs for all of NP? So specifically, we want the proof size, again, to be polylogarithmic in the huge instance size, polynomial in the small witness size, and we still want to have a constant query complexity. So for this question, our main results show that we do have succinct PCPs for the entire class of NP under standard assumptions. We showed it by constructing succinct PCAs for all of NP, and in our construction, our PCA construction is also publicly verifiable, which means that any verifier given the CRS can verify the proof. You don't need any inner state or private key, and also has adaptive soundness, which means that the adversary can choose the instance according to the CRS, adaptively according to the CRS. And we also have succinct prover, which means that our prover is efficient, in particular for a relation that is verifiable in deterministic time t and space s given the witness. A succinct prover will run in time that is quasi-linear in t, polynomial in the small witness size, and will use space that is linear in s and polylogarithmic in t and polynomial in the witness size. Now, comparing our results to previous results, we're the first to construct succinct PCAs for the entire class of NP. We also achieve publicly verifiable PCA, adaptively sound. And in addition, we instantiate our construction under standard assumptions, whereas previous work relied on sub-exponential hardness assumptions. And in addition, we also get a succinct prover, which means that the prover is efficient. Now, our PCA construction actually relies on two main objects, RAM delegation and PCPP. We're going to define RAM delegation now. So in RAM delegation, we think about a RAM program. In this setting, we think about the input to the RAM program as a pair, M and Y. So we think about M as huge. It might even contain the entire computation of the RAM machine. And we think about Y as small. Now the RAM machine on M and Y outputs B, so the prover gets M and Y as input and wants to prove to the verifier that the output is B. So the prover sends B together with a proof to the verifier. Now the verifier who wishes to verify the deterministic computation efficiently gets only a digest, only a small representation of the huge input M and explicitly Y, the small input Y. And for the efficiency parameter, we want both the proof size and the verification time to be polylogarithmic in t, in time of the original computation, and polynomial in the small input y. Now, what I want you to remember from this slide is that the verifier actually verifies a deterministic computation without even reading the input to the computation. So it only needs a succinct representation of the input. Now, previous work on RAM delegation schemes so there's many work on RAM delegation schemes. Previous work only achieved a subset of the properties that we need for our PCA construction. So therefore, we constructed a RAM delegation scheme that combines all of those properties together. For this talk, when we describe the high-level description of our PCA construction, we don't need to get into the details of each property, but any of you who is familiar with RAM delegation can recognize the properties. Okay, so we saw PCA results, our RAM delegation results, and now we are ready to move on to the PCA construction. So we use RAM delegation, mainly RAM delegation and PCPPs. We start by a naive attempt of our construction. So we have a relation. Now we have a prover and a verifier. The prover has access to the witness. So the first thing that the prover can do is just send the witness to the verifier. Now this proof is succinct. The verifier can verify the proof by using the NP deterministic verifier. So it just checks that mxw equals 1. So we have perfect soundness, we have succinctness. The problem is that the verifier needs to read the entire witness, which means that we don't have constant query complexity. Now, a standard approach to solve this problem is use PCPPs for this computation. So PCPs are PCPs of proximity. In PCPPs, we think about the instance as a pair, x and y, where x is explicit and y is implicit. The verifier has only Oracle access to y, to the second part of the instance. Now, for the completeness, we say that the verifier generates a proof. The prover, generates a proof and sends it to the verifier. The verifier verifies that x, y is in the language by querying only a small number of bits from both the proof and y. So if x, y is in the language, then the probability that the verifier accepts an honestly generated proof is 1. Now, for soundness, since the verifier has only limited access to the instance, we would not expect him to, so we would expect him only to catch instances that are far from the language. For that, we define Lx, where Lx is all the y's such that x, y is in the language. And for any prover, even computationally unbounded prover, that generates an instance x, y, where y is far from Lx, it also generates a proof, the verifier will accept the proof with probability less than half. Where y, I said that y is far from Lx, right? Okay, good. So what does the verifier actually wants to verify? So if the language is decidable in time t, in deterministic time t, using a machine m, what the verifier actually wants to verify is that mxy equals 1 while having a limited access to y. So we do have PCPPs. PCPP theorem says that for any language that is decidable in time t, the proof size is going to be large, it's going to be polynomial in t, and the verifier makes only constant queries to the proof. So using this PCPP object, we want to verify that mxw equals 1, but we don't want to read the entire witness. So the prover generates a PCPP proof, sends it to the verifier, and the verifier, using the PCPP verifier, can verify that mxw equals 1. So we do have constant query complexity, we do have soundness. The problem with this approach is that the proof size is going to be too large. So the PCPP proof size is going to be polynomial in t, in the time to compute mxw, and m at least reads x. So t is larger than x. So it's going to be, the proof size is going to be polynomial in x. And this is too large, this is not succinct. So we're going to take a step back, remove the PCPP layer, and now we want to verify deterministically that mxw equals 1 in time that is less than x. So we can't even read the instance. Luckily, we have RAM delegation. So in RAM delegation, again, verifier gets a digest, a small representation of the instance, and can verify the deterministic computation. So we think of M as a RAM machine. Now, in this setting, we have a CRS. The verifier can generate the succinct representation of x, the digest of x, in advance. The prover sends the witness together with the RAM proof to the verifier, and the verifier just runs the RAM verifier on the digest of x, the witness, and the RAM proof. Now we're going to move forward, and so the RAM verifier runs in time t prime, which is polylog in x, and this is good for us, and we can use again the PCPP. Now we're going to use the PCPP on the RAM verifier computation, which is fast. So the verifier can compute the digest of the instance x in advance, and then the prover can, again, send the witness together with the RAM proof, and then a PCPP proof that the RAM verifier would have accepted the proof. And the verifier can run the PCPP verifier. Now we have succinctness. And we also have constant query complexity. But the problem with this is that we actually don't have soundness. And why is that? So it comes from the computational soundness of the RAM verifier. So the RAM verifier, so it's computationally hard to find a proof that will convince the RAM verifier, but it might be efficient to find a proof that is close to a proof that would convince the RAM verifier. And this, the PCPP soundness does not catch. We only catch words that are far from the language. So to solve this problem, we add error-correcting code to the witness and the RAM proof, and this kind of make each code word far from each other, and this solves the problem. So we actually have computational soundness. We have also succinct proof and constant query complexity. Good. Okay, for summary, we actually got, so we got succinct PCA for the entire class of NP under standard assumptions. We have new delegation scheme, which is both complexity preserving, has strong soundness, support read-write RAM machines, and has explicit and implicit syntax. And for the open problems, so Bonman and Rothbaum actually showed that succinct PCAs for the entire class of NP would have implied a computational analog of instance compression. So now that we have succinct PCPs, we also have computational instance compression. And they also showed that actually PCA implies hardness of approximation results. And the actual results were not surprising since we also get them from PCPs. But the surprising part was that PCA, which is a computational object, implies hardness of approximation results. So the question is, now that we have succinct PCAs for the entire class of NP, can we get new hardness of approximation results? Another question which I find interesting is, can we get PCA that is both succinct and zero knowledge? And for the last question, so what happens if we add interaction to the PCA? Can we get PCAs from one-way function, for example? That's it. Thank you very much.
So we have time for questions. If you have a question, please come up to the microphone in the front.
With the move from perfect statistical soundness to computational soundness, you also introduced the CRS. Is this like inherent, or would computational soundness also help if you didn't have a CRS?
I need to think about it, but I think if you remove the CRS, then you don't have computational soundness, and you can show that it's information theoretic, and then you have the how do you say it? So you have succinct PCPs implies polynomial hierarchy collapses, so you can't get stronger definition of soundness, at least not information theoretic. So I think it's kind of inherent. Yeah.
Okay, thank you.
Hi, great talk.
Hi, Shavik. Thank you.
So what do you hope to achieve if you add interaction? Because, for example, I think, I might be mistaken, but don't Kalairas do interactive PCPs that are succinct, for example?
So IOPs, you mean?
So what do you mean by interactive PCA, I guess? Maybe that's the first question.
Yeah, so it's either computational analog of IOP,
Okay.
or you can think about it as the interactive analog of PCAs. So you have computational soundness and you have interaction. So we might get something even more succinct, but I think that, yeah, I guess it's about getting something maybe sublinear in the witness, or even more succinct. Mm-hmm. But the point is that you get something better than IOPs and also from simpler assumptions than the PCA that I constructed.
I see. Okay, so, yeah.
Okay,
Thanks.
thank you.
Hi, thanks for the talk. So maybe I'm missing something. So why, since you're in the CRS model, why it's not straightforward to achieve zero knowledge via NISIC by applying
Zero knowledge via what, sorry?
By using a non-interactive zero knowledge proof system, by like
proving in zero knowledge that you have an accepted?
I need to think about it. I tried it. I think it just makes somehow the proof larger. So it will not be polynomial in the witness anymore. The point is to get succinctness together with the zero knowledge. But we can think about it later. Yeah.
Thank you.
Okay, thank you.
So let's thank Shani again.
Oh, sorry.
So the next talk is software with certified deletion, and this is by James Bartusek, Vipul Goyal, Dakshita Kurana, Giulio Malavolta, Justin Reyes, and Bhaskar Roberts, and Justin will be giving the talk.
Thanks for the introduction. So, as you mentioned, this is a joint work with a number of wonderful collaborators. And let's imagine that a user wants to store their data, but they don't want to actually host their own server. One option is to store it in the cloud. Of course, this runs the risk of the cloud server learning your data. So the natural solution to this is to simply encrypt your data. And now you store it on the cloud. The issue with this is that the data might still be recoverable if either you lose your secret key and it's stolen somehow, or if the encryption scheme is broken. Now, I know you all have your favorite hardness assumptions, but they are just that, they're hardness assumptions. And we don't know when the next one's going to be broken. We recently had a big scare with LWE, but thankfully it's still intact. With a classical ciphertext, there's not really much we can do to get around this problem. But intriguingly, the possibilities change when we move to a quantum ciphertext. So now we can have the possibility of actually deleting the data, where the server does a destructive measurement, and if they do this measurement, then the data becomes information theoretically hidden, even if the encryption scheme is broken later, even if the secret key is leaked. The other nice part about this destructive measurement is it generates a certificate that you can give to the user to convince them that you actually have done this destructive measurement, or at least one that's close enough that it still destroys the data. Previously, some very nice works constructed encryption with certified deletion. And this just allows the server to store the data and then delete it later, but there's nothing else that it can do. In this work, we show how to actually compute on the data and then provably delete it. I would like to mention that some prior works did construct fully homomorphic encryption with certified deletion. However, the very act of doing the evaluation actually prevents you from deleting it, and in order to then do the deletion, you need some additional interaction, which has its own issues. We give a generic compiler that allows repeated access, or repeated partial access to the data, and it can be applied to a wide variety of primitives. It gives us our, at this point, standard certified deletion guarantee, where before we delete it, you have computational hiding. And after you delete the ciphertext, it's upgraded to statistical hiding. And this includes even with key leakage. There are two main motivating applications for the ability to do computation on the data. The first is in the interactive setting, where we're going to give out, or we're going to ask a server to do a computation for us, and then they send the result back. This gives us blind delegation with certified deletion. And as I mentioned previously, some prior work did think about FHE, which allows you to do blind delegation. But the issue with this is that the additional interaction that you have to do in order to do the deletion after evaluation provides some opportunity for the server to learn something by deviating from the protocol. So we achieve, for the first time, a construction with security against a server that might deviate from the protocol. And for this, we just assume LWE. In the non-interactive setting, where we just give out a program to somebody and they can locally evaluate it as much as they want, we introduce obfuscation with certified deletion. which just assumes indistinguishability obfuscation and one-way functions. Now, I know I've skimmed over these very quickly, so let's go into the details a little bit more of what they are. In blind delegation with certified deletion, we have a client over here, the smartphone, that asks the server to compute a function on their data, and then asks the server to delete the data. So we've got our key, we encrypt the data, and send it along with the function to the server. The server then evaluates it and returns an encrypted ciphertext of the evaluation to the client. At this point, the client now asks the server to delete the data, and the server hopefully will comply, and we can detect whether or not they did comply. If they did, then the information is completely deleted. And our construction uses post-quantum FHE as well as snarks for P, both of which can be implemented from LWE. Now let's talk about the non-interactive setting. A very motivating scenario is if you have a company that wants to rent out its software to users, but maybe it doesn't want to pay the cost of running all the computations locally, so it doesn't want to run it as a service. An interesting option is to be able to encode the software somehow and send it to the user. And now the user can locally evaluate it as much as they want. And for each month that goes by, the company charges the user. Then, when the user is done evaluating it and no longer wants to rent the software, it can delete it and convince the company that it's deleted the program, so the company stops charging them. This scenario has been previously studied under the name of secure software leasing, but there are a few issues with the original definition, which I'll get into in a little bit. For now, let me start by defining differing inputs obfuscation, which will help us on our way to defining obfuscation with certified deletion. So let's imagine that we have two circuits, pi 0 and pi 1, where they are the same on all except one input, y star. But even given the two circuits, it's hard to find this input. Then we can imagine a security game where the company or the challenger picks one of these two circuits at random, obfuscates it, and sends it to the adversary. Then the adversary tries to figure out which of the two circuits it is. And this should be hard to do. Now, let's go ahead and add certified deletion to it, the game. The first change that we're going to make is now the obfuscated program is going to be a quantum state. And the second change is we're going to add a deletion step in the middle. So the adversary will now, after it receives the obfuscated program, it will delete it. Note that it can evaluate as much as it wants before it deletes it. And then after the program is deleted, if the certificate is valid, then the challenger is actually going to reveal the differing input. And at this point, the adversary tries to guess which program it is. Now, I'd like you to note that if the adversary could continue to evaluate the program, after y star is revealed, it's very easy to determine which of the two programs it is. You just run the program on y star and check which input it which output it matches. So this really does say that after you've deleted, the adversary can no longer continue to evaluate the program on these protected inputs. Aside from our two main motivating applications, I'd like to talk about a couple of other ones that are kind of offshoots of these applications themselves. The first one is strong secure software leasing. This goes back to that slide I showed just a couple of slides ago, where the user is renting software from a company. And the idea here is that if the adversary returns an authenticated copy of the program, they can't continue to evaluate a local pirated copy. Now, I'd like to mention that in the original definition of secure software leasing, the pirate copy cannot be honestly evaluated. So there's an honest evaluation procedure, and if the adversary continues to follow that on the pirated copy, it doesn't always work. In our strong version, we go beyond that to actually guarantee that no matter how the adversary is evaluating its pirated copy, it can't get any information out of it. The second application is crypto systems with revocable keys. So let's imagine that you're going on vacation, you want to temporarily allow your secretary to read your mail. I know we all have secretaries. I look forward to the day when I can one day have a secretary to read my mail. Of course, after you come back from vacation, you don't want your secretary to continue to read your mail, right? So what we want to guarantee is that after the secretary has deleted their temporary key, the new ciphertexts that are generated have semantic security still. And we give a general way to achieve this that can be applied to public key encryption, functional encryption, and more. As a final application and a byproduct of our main technical contribution, we also construct publicly verifiable certified deletion, where anyone can check the certificate of deletion. Now, a couple of follow-up works have significantly reduced the assumptions from obfuscation to just one-way functions, which is very, very nice. So now I've given you an overview of our results. Let's talk about how we actually achieve certified deletion. I know not everyone here has a background in quantum cryptography, so I will try my best to give a general overview of the techniques in an accessible way. So a quantum state is simply a unit vector, and we can present it in a couple of different bases. For now, there are just 4 different states I'd like to focus on. In the first 2 states are in the computational basis. So it'll be either a 0 vector or a 1 vector. We can also think about states in the Hadamard basis, which are plus vectors and minus vectors. And the nice part about the Hadamard basis is it's kind of halfway in between. A plus is halfway in between a 0 state and a 1 state. And a 1 state is also, a minus state is also halfway in between a 0 state and a 1 state. So what this means is that the 2 bases are somewhat incompatible. And let me explain that a little bit further. The idea is if you measure in one basis, then you actually destroy data if it was previously encoded in the other basis. So here we have, let's just focus on the top line. We start with a 0 state and we measure it in the Hadamard basis. This gives us a result of either plus or minus, and since we started with a 0 state, it will give us each case with probability 1/2. So independently of the original state, whether it's 0 or 1, we get the same output distribution. And a useful fact about quantum measurements is whatever state that it tells you it is, that's what it's become. So we've now actually destroyed the data. It's become completely random. Certified deletion from prior work has used this idea where they encode the data in the computational basis, and then the hope is to force the adversary to measure this in the Hadamard basis when they delete, and this would destroy the data. To ensure this, we add some random check positions in the Hadamard basis, and a verification key tracks where these check positions are. So here we have the data positions in the computational basis in orange, and the check positions in the blue Hadamard basis. And as I mentioned, to delete, the server should measure the whole thing in the Hadamard basis. And for all the locations which were originally Hadamard basis states, they're blue, the outcome is deterministic. But for all of the orange computational basis states where the data was encoded, it becomes random. Now, the outcome of the measurement actually gives us our certificate directly. And to verify it, we just check all of the check positions. So we line up all the blue indices and verify that they match what we're expecting. And intuitively, because they're mixed at random with the data positions, the adversary doesn't know which positions are safe to avoid measuring. The issue when we start to look at computing on the data is one of malleability, because the adversary can guess, let's say, a single data position, It succeeds with some 1/poly probability, and then it flips it. And this is problematic if it succeeds, because now it can evaluate a slightly different message. And in the case where it gets the output, this immediately reveals a lot of information about what the message is, because it can evaluate actually on both possibilities. And even in the case where we don't immediately reveal the output, but we're doing blind delegation and do some additional interaction with the client to ensure deletion, it still can leak some information. In order to prevent this, we really need a method to verify that the ciphertext is the original ciphertext and that the underlying data hasn't been modified. I'd like to note that if we just gave out an oracle that checks all the Hadamard positions and verifies that the computational data positions are not modified, then this is completely insecure. So we need some new ideas. The second attempt uses a class of states called subspace coset states. The advantage of these is that the qubits are highly entangled. So later on, we'll be able to actually publish an oracle for membership without worrying too much. So let's imagine that we have a subspace of all bit strings, and then we have an offset V, which is chosen from a group of unique coset representatives. Then we can look at the coset S plus V and define a coset state, which is just an even superposition over all possible vectors in the coset. There's an additional phase term here. Don't worry about it too much. Let me just tell you what it helps us do. What it does is we can actually now take the original coset state and transform it using a quantum Fourier transform. And now it becomes another coset state for the dual coset, which is S perp plus W here. And so this is going to give us our deletion certificate now, because remember that the idea behind deletion was to measure in the Fourier basis. The useful fact about subspace coset states is that we can publish oracles to check membership in the subspace cosets. And this is actually secure because the oracles hide some information about the subspace. Let me define that a little bit more carefully. So let's imagine that we have some distribution Z, and we evaluate it on S. This should be indistinguishable from evaluating the distribution on a random superspace of S. As an example, a membership oracle for S is subspace hiding, and this holds even if it's implemented using indistinguishability obfuscation. Now, let's move to certified deletion with coset states. Imagine that we give the adversary a subspace state, as well as a random supercoset, T plus U of S plus V. We give them some subspace hiding distribution, and we give them an encryption of the bit, the data B, which is masked by the parity of V. Then the adversary outputs a certificate as well as some residual state. What we want for security is if the certificate is in the dual space, then the residual state is independent of what B is. To give you a very quick idea of how to use this for obfuscation, let's imagine we have an I/O program which has hard-coded the space S, a random superspace, and a masked program pi. On input and input X and a vector Y, we check that Y is actually in T plus U. And then we use it, if so, we use it to compute V, which we can do correctly if Y is in S plus V. And intuitively, it's hard to find a vector that will pass this check without being in the correct space. Then we can use this vector to decode V, or decode pi, and evaluate the program. Thanks for listening, and if you have any questions, feel free to ask or see our paper on ePrint.
have time for a very quick question. Okay, I'll just ask one.
Sure.
So your data is classical, right?
Yes, the data is classical.
Do you have any thoughts about what happens if the data was quantum?
If the data is quantum, then we have to start thinking about obfuscation for quantum states or quantum circuits. There's been some work on that recently, but it's still very much a very open area. It's a very interesting topic for certain.
Okay. Yeah. So let's thank Justin again. So the next talk is Public Coin Complexity Preserving Succinct Arguments of Knowledge for NP from Collision Resistance by Cody Freitag, Omar Paneth, and Rafael Paz. And Cody will be giving the talk.
Thanks. All right. Okay, so yeah, this is joint work with Omar Paneth and Rafael Paz. I'm Cody Freitag, and the title has a lot of adjectives lying around, so I want to start by just motivating the overall area of cryptographic proofs for NP. And to start, what do I even mean by NP? So this is the class of languages L for which there's a prover that can convince a verifier that some statement X is in the language L, and we call this proof usually the witness W. We require the standard notions of completeness and soundness. If X is in the language, the witness should convince the verifier, and X is not in the language, there should be no such witness. And I can think of this kind of in two different ways, either in terms of kind of non-interactive proofs, like I've written here, but this is also equivalent to think of it as kind of generic non-deterministic computation, where this witness W you can think of as the non-deterministic choices for the NP verifier V. And with this kind of view in mind, throughout the talk, I'll think of this NP verifier V as a RAM machine that runs in some time t and some space s, thinking of it as a RAM program. So this is what NP is. What is a cryptographic proof for NP? So I like to think of this as a compiler that takes a non-interactive proof that we had above and turns it into a potentially more complex cryptographic version that may include some interaction. The new cryptographic verifier may flip some random coins. And I want this compiler to be generic. So when I say a proof for NP, I want it to work for any arbitrary language rather than a specific fixed language. And again, you can think in kind of two ways. Either you're proving the original statement, or it suffices to think of the cryptographic prover as proving that the NP verifier would have accepted the witness as provided. So in this cryptographic setting, we often relax soundness while keeping the same standard completeness notion, and we require that for X not in the language, it just soundness only holds against polynomially bounded provers. And even more, we'll usually consider a stronger notion called argument of knowledge, which says if such a prover does convince the verifier, then it must actually know a corresponding witness, although I won't get into this notion for the purpose of this talk. And then a last kind of optional property that's nice to have for a lot of these proofs is that it's public coin, meaning that in this interactive protocol, the verifier only sends random coins and maintains no other private state. So why do we do this whole process? Why do we compile this kind of nice, clean, non-interactive object into this cryptographic version? Well, usually there's two main goals that we care about. Some notion of privacy, where we're hiding some information that may be sensitive about the witness, or we're trying to get better, improved efficiency relative to the original non-interactive proof. So again, I use these time-bound T and space S for the original NP verifier. The idea is when this time-bound T, for example, is very large, maybe we can get something that's much more smaller in terms of the concrete efficiency for the verifier and communication. And this efficiency notion will be the focus of this talk. So specifically, I want to kind of categorize the various aspects of efficiency into three categories. So you could ask for the kind of communication, the bandwidth of the interaction be very small. The verifier, the new cryptographic verifier V prime, should be much more efficient than the original time-bound T. And also along the way, we want to make sure that the cryptographic prover kind of is scalable relative to the original computation. So if we just focus on these first two properties and ask for kind of the proof to be polylogarithmic in the time-bound t and the time of the verifier to be also polylog in t and potentially polynomial in the instance size x, then having these properties together, we typically refer to this as a succinct argument. And in fact, for over 30 years, we've known how to construct succinct arguments for all of NP, only assuming collision-resistant hashing in just 4 messages. So a very simple interactive protocol. And I want to point out in terms of assumptions, we only kind of rely on the most basic form of cryptographic assumptions that are like unstructured, like any random enough function is likely to be collision resistant. And these sort of assumptions live in what's called mini-crypts that aren't known to imply kind of higher forms of cryptographic primitives like public key encryption. So at a very high level, the way that this protocol works is it's a compiler that takes any information theoretic object of a probabilistically checkable proof, compiles it using commitments of hash trees that are succinct and have specific properties, and is able to turn this into a argument with very low bandwidth and an efficient verifier. But the issue, at least with the kind of original probabilistically checkable proofs, is that the prover needed to kind of compute these objects ran in time that scaled polynomially with t. And so if we're thinking of the NP verifier's time t as very large, this ends up being not scalable whatsoever. So as a result, there's been a ton of work over the past 30 or so years trying to make the prover more scalable in these kind of succinct protocols. So one way you could try to do this is by creating more efficient PCPs, kind of taking this information theory object and having the prover compute it in much quicker time. There's been a lot of work on this, but from a practical and even theoretical perspective, this still isn't quite where we want. So there's been works kind of using interaction to make these sorts of objects even more efficient, or giving structure to these information theoretic objects and introducing new cryptographic compilers for these objects, which has actually been kind of the bulk of a lot of the forefront on scalable provers for these objects in practice. There have also been some more generic techniques like recursive composition, where you kind of incrementally update an existing proof for your computation kind of along the way. The downside of some techniques like this is it often relies on strong cryptographic assumptions like knowledge assumptions or idealized models like random oracles. There's some other ways to try to optimize certain aspects of the prover's efficiency. For example, we had some work trying to make the prover's running time kind of as close to t as possible at the cost of some additional parallel processors. But the last notion that's been studied that I want to focus on for today is the question of the space efficiency of the prover, which is often called the complexity preserving protocol. So to motivate the reason why space efficiency is important, I want to give a very high-level blueprint for what I'll call Killian-based arguments that a lot of the previous protocols kind of fall into this framework. So the idea is you first write down the tableau of the computation, you encode it in some way, and then you cryptographically commit to this encoding in order to give the verifier access to this encoding in some way. And the issue with this kind of general approach is kind of naively, as I've presented it here, writing down this tableau or this encoding kind of inherently requires space that grows with the time bound of the original NP verification time. And so this is a natural question: can we do something like this or do something equivalent to get succinct arguments where the space of the prover P prime scales with only the space of the underlying computation instead of the time-bound T, especially for computations where the space is much smaller than the time-bound of the computation? And so this is what a complexity-preserving argument asks for. It's a protocol where this transformation for any NP language has a cryptographic prover that runs in time essentially t and space essentially s, kind of matching the underlying computation up to kind of polylog factors. And yeah, this is kind of the best you could hope for, up to kind of polylog factors And throughout, I'm also kind of ignoring polynomial factors in the security parameter. So this object was first studied by this work of Potansky and Chiesa, where they construct kind of 4 message complexity preserving succinct arguments from fully homomorphic encryption. And this is a nice protocol. It matches Killian's protocol in terms of the round complexity, the succinctness. However, there's kind of 2 main open questions that they left from their work. The first is that of public verifiability. So the way they use FHE, the verifier needs to kind of maintain a private key that it used to decrypt answers in some way. And so their resulting protocol is only privately verifiable and not public coin, for instance. And the second, they rely on kind of heavier cryptographic assumptions than Killian's original protocol. They assume FHE, which kind of lies in cryptomania, implies public key encryption, whereas kind of Killian's original protocol only assumed CRH. So there's been a number of works that have tried to address some of these questions and kind of further the progress on complexity preserving succinct arguments. And I'll kind of look at the landscape in kind of broad terms and categorize them in kind of into 3 of the following buckets. So the first line of work focuses on, or ends up doing this by using non-standard assumptions. So this ranges from kind of knowledge assumptions like snarks, random oracle models, or class groups, which have been less studied in cryptography. The second bucket I want to mention focuses on kind of the stronger requirement of having non-interactive protocols, but then only works for deterministic languages in P as opposed to all of NP. And so there's been a number of works that have looked at complexity preserving protocols in this regime. And this is culminated in works that construct these objects from kind of generically bargs for NP, which at this point are known from LWE, bilinear maps, and sub-exponential DDH. But I want to point out, even in this case where we only are doing things for deterministic computation, but non-interactively, these are all still cryptomania assumptions. So even for P, we don't know things from mini-crypt type assumptions at this point. And then the last work that's quite related to our motivation here focuses on the black box use of CRH. And here they get a really nice protocol where the communication and verification are non-trivial, so they're less than the kind of naive communication of the original non-interactive proof, but they're still not fully succinct. So the communication scales as T over S, and the verification time scales as T over S plus S. So kind of thinking of the best case scenario where this space S is root T, this still results in communication and verification that are kind of square root T, as opposed to polylogarithmic in T. And in some, they show in this work that this is in some sense tight with respect to black box constructions, showing that kind of if you can do better than this, it would imply certain codes with good distance that seem infeasible. So our main result is kind of getting around that last paper I mentioned by using non-black box techniques. And specifically, we show there exists public coin log-based lambda of T message protocols that are complexity preserving and succinct for NP, only assuming collision-resistant hashing. So at this point, hopefully all of these adjectives make sense. And I do want to take a second to focus on the round complexity here. So to think of this, if T is any kind of fixed polynomial in the security parameter, then there exists a corresponding constant that bounds the message complexity of the protocol. But on the other hand, there's no fixed universal constant like 4 or something, like in Killian's protocol, that bounds the message complexity here. In terms of the questions from the work of Potansky and Chiesa, because our protocol is public coin, we get public verifiability, and also we only assume collision-resistant hashing, which is a mini-crypt assumption, kind of matching Killian's protocol from before. And in terms of remaining open questions, it's interesting if we could do the same sort of, get the same sort of requirements, but only with fixed constant rounds. Again, the goal being to try to match Killian's protocol in the complexity preserving world. And then there's some other kind of more technical questions, whether we can get not just succinct arguments for NP, but universal arguments that can scale to prove arbitrary exponential time computations soundly. Another subtlety is that we kind of start with a RAM verifier and get a RAM prover at the end of the day. If we start with a Turing machine verifier, can we get a Turing machine prover as well that's still open? So before I spend a little bit of time describing the high-level idea of our result, I want to mention a few corollaries. So first, there's a generic transformation to make this protocol zero knowledge. This follows from a classic technique from the 80s, where you first commit to the messages in the protocol, and then prove in zero knowledge that you know corresponding prover messages that would have caused the verifier to accept. This is kind of known as the commit and prove paradigm, and can generically give zero knowledge. The second, I mentioned before, this work on parallelizability. So we gave a generic transformation that can essentially make the prover's running time almost exactly the same as the original NP verifier running time t at the expense of some parallel processors. So this is a generic transformation that only relies on CRH, so we get kind of similar results to this theorem. And the last thing, because our protocol is public coin, we enjoy various properties like being able to make it non-interactive in the random oracle model. And this just follows from the Fiat-Shamir transformation. And I want to point out that even the previous constructions of snarks, where snarks are built from random oracles, the way they use recursive composition means that their eventual complexity preserving argument can't be proven in the random oracle because it requires this kind of weird heuristic step where you first instantiate the random oracle, then prove about this instantiation, and so on and so forth. So our protocol, after being compiled, gives the first protocol that is only that can be proven secure from random oracles, plus other mini-crypt assumptions. Okay, so with the remaining time I have left, I want to give a very high-level overview of the main ideas for how we get our construction. So to start, I'll give kind of a new non-trivial space protocol. I'll show how to kind of remove this square root t factor and get a solution for at least small space. And then the last step is to extend to arbitrary space. And this last step is actually quite common for RAM delegation and has been known since this work from Kalai and Paneth back in 2016. So I'll just focus on the first two steps. Okay, so the first step is quite a simple observation. And the idea is, instead of kind of proving the entire computation in one go, using something like Killian's arguments, we're only going to break the computation up into several parts and prove each of them independently. So we'll construct these new, I'll call them K substatements, state 1 to state K, and we'll kind of, in parallel, prove all of these at the same time. And so if you look at kind of the efficiency for such a prover that does this in parallel, kind of because you're cutting things into pieces and proving each of them, if you start with something that's quasi-linear and space-preserving, you'll essentially get something that maintains that. And then the point is, in terms of space, we can kind of build each of these proofs in each round independently, and so we only have to pay for the space for one of these subprotocols at a time. And so when you balance out kind of what you should set this parameter k to be, how many substatements you split things up into, you end up with a prover that has space that scales with t square root t instead of t, which is the naive protocol. On the downside, we've now blown up the communication and verifier efficiency. Because we're kind of separately proving k statements, our verifier and communication efficiency will grow with this parameter k, which we set to be root t. So this gives something kind of slightly non-trivial and new, but the question is, can we kind of push this further, and instead of getting this t to the 1/2, push down to polylog t in all of these parameters? So specifically, I'm going to think of addressing kind of communication and verification with one technique and the prover space with another. So for communication and verification, we're actually going to use a similar commit and prove paradigm that I kind of mentioned before for zero knowledge. And the idea is, here we're using the succinctness of the commitments to prove to kind of commit to all of the prover's messages for some protocol that can be generic and just gives succinct messages for all the prover messages. And then we can use a succinct proof like Killian to then prove that you know corresponding prover messages that would have convinced the verifier. And I'll show a brief example in a second for how this works. And the last step is because our prover kind of only ran in the space of one subprotocol at each step, if we use a more efficient subprotocol like the one we just built, we can very quickly reduce the prover's overall space. So we'll do this via recursion. So very quickly, I'll just show what this looks like. So in our kind of recursive protocol, where we have like a sequence indexed by this parameter r, the verifier will first send over a hash function. The prover will compute these kind of substatements, commit to them using this hash, and then we'll run each message of the underlying verifier. The prover will compute the corresponding message for each substatements, send commitments to them, and we'll repeat this for each message of the subprotocol until at the end we finally finish this commit and prove paradigm and have the prover prove that it knows corresponding messages that would have convinced the previous verifier for each substatement. And so very high level, I know I went through this quickly, this is what our eventual protocol looks like. And yeah, the point is that because we're just using a random hash function and a public coin succinct argument at the bottom, this will kind of maintain the public coinness of the protocol at each step. So yeah, that's all I wanted to say, and thanks for listening.
We have time for a very quick question.
So you said that the polylog fractal in the efficiency is inherent, right? Do you have lower bound for that, or just inherent in your construction?
I didn't claim that it was inherent.
Oh, sorry.
Just
So
kind of, if you're hoping for something that's good up to polylog factors, that's what we aim for, but there's potentially a way to maybe get just linear time or improve that.
okay, thank you.
Yeah, that'd be interesting for future work and to make it more practically efficient.
Okay, so let's thank Cody. And let's thank all the speakers in the session. We have a coffee break now.